We want to welcome everyone here in the lecture hall and at home who's watching on the live stream. Saturday Morning Physics is supported by the University of Michigan Physics Department, by the Lois Tiffany Endowment, by the Tomazawa Endowment, the Van Loo family, Saturday Morning Physics Fund, and the Gail Farley Bequest. And I wanted to let everyone know that March 16th next week is all day Giving Blue Day. And if you'd like, you have the opportunity to support undergraduate research here at Michigan, as well as Saturday Morning Physics. So go to umich.edu to find that. So today's lecture, we'll have a question and answer period at the end. If you're in the audience here, you can write a question on a card, or at home, or even in the audience, you can also send an email to physics@umich.edu with your questions for our speaker. Our speaker today is Professor Michael Meyer. He is a professor in the astronomy department here, but he grew up in rural Missouri and then did his undergraduate work at Washington University in St. Louis and his PhD at the University of Massachusetts at Amherst in astronomy, receiving the PhD in 1996. He then did postdoctoral work in Germany, in Heidelberg, at the Max Planck Institute for Astronomy, was a Hubble Fellow at the Stewart Observatory at the University of Arizona, and also faculty there until 2009. Then he went to Switzerland, to ETH in Zurich, until 2016, and then he came here to join us at the University of Michigan, and he has been a professor of astronomy since 2016. So we're really excited to have you here for this most timely topic, which is the James Webb Space Telescope Discovery Space. Thank you very much for coming, Michael.
5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
All right, that's enough of that. Couldn't resist. It's been a long time coming, as many of you know. And it's always fun to hear them count down in French instead of our usual NASA launches. Thanks very much, Tim, for the introduction. It's great to be here and to tell you about this amazing observatory, maybe a bit of hyperbole in the launching from the jungles of French Guiana to the edge of time itself, but we'll see how the mission pans out. What I'm going to try to do this morning is to tell you a little bit about the history of the origination of the observatory, show you some of the amazing technical feats that were required in order to build it and get it together and ready for that incredible launch on Christmas morning late last year, and try to give you some insight into the science that we look forward to getting. Unfortunately, I will show you some images, believe it or not, but not of the science that we hope to do with the observatory. And I'm hoping that one of my colleagues will be able to come back and tell you about the science that Webb is doing in the next couple of years. Okay, so let's get started. First of all, I want to explain why we go into space. So if Monica can show my star field over here. We like to take fine, detailed pictures. Many of you will have phones with cameras in your pockets that actually take pretty incredible images these days. We have big telescopes on the ground that can take pretty nice images too. Here's just an example of what a star might look like, and imagine the one on the left is a star with a planet around it. So it's close by and fainter. And because of the roiling in the Earth's atmosphere, the turbulence in the Earth's atmosphere, the quality or fineness of detail in our images is degraded significantly. You can see these columns of air passing up in front of this little telescope. And as the air heats up, it gets to be that we cannot separate the light from these two things, the faint thing near the bright thing. I study star and planet formation, how stars like our sun formed and how planets like Earth and Jupiter formed around stars like the sun. And eventually we want to, take spectra of planets around stars like the sun and see what's in their atmospheres and wonder someday whether or not we could discern the signatures of life in an atmosphere of another world. But when things get blurry like this, it gets incredibly difficult to separate out the things that we want to see. So our spatial resolution can be limited by the atmosphere on the ground, and that's why it is really wonderful to go to space and to be able to use space-based telescopes like the Hubble Space Telescope. There probably was a public lecture in the early 90s here about HST when it went up, and to our horror, finding that the mirror had been made perfectly but a little wrong. Fortunately, we were able to put corrective lenses like I need at 54 so that I can see. But Hubble, a venerable telescope, which is arguably the most productive visible infrared telescope that we've ever created. It's made tremendous discoveries in all manner of fields, from star formation to understanding how planetary systems form, to trying to observe galaxies as close to the edge of the universe as Hubble can get. It's made a heroic attempt to get out to ages of order 1 billion years after we believe the Big Bang and the universe formed. But that's kind of where it runs out of steam, and it can't do much more than that. So it was already recognized in the early to mid-90s that we needed to start planning for the future. None of us, I think, realized how far into the future that future would be, but we're there today, and so we celebrate that. I was very fortunate, or cursed, very early in my career to get dragged in to looking at what a design of a future space telescope might be looking like. And this is a picture of a younger and lower mass me in the back there in this committee, no windows, right? You're stuck up in a hotel somewhere for 36 hours arguing about things. But we were trying to figure out what the next generation space telescope would look like. And because one of the primary things that Hubble was trying to do is to see back far into the early universe and understand how the context of large-scale structure formation from cosmology led to the formation and evolution of galaxies and ultimately to us, we realized that you have to go into the infrared. The light from these distant galaxies gets stretched out as the universe expands, and so all of the wavelengths of light that we're used to studying for galaxies get shifted into the infrared. The plan was for this telescope to be from 1 to 5 microns. So think of a micron as redder than the reddest thing your eye can see, and 5 is 5 times farther than that. This is a plot of how bright our sky is. So high is bad in this case because it provides a source of noise and distraction against what you're trying to see. So this is a plot of that sky background from 1 micron to 10 microns. And this is, again, where the focus was. But you can see that the space background, here shown in red, is many, many factors of 10 or orders of magnitude lower than the background from the sky. So this big open space here is what we refer to as discovery space. We simply don't even know what we can see because the space-based background is so many orders of magnitude. It would take 1 million times longer to try in vain to make an observation from the ground of what the James Webb Space Telescope could do routinely. And so this was recognized as a huge opportunity to do great discovery in space with JWST, what was then called NGST, the Next Generation Space Telescope. This is also showing the transmission of our Earth's atmosphere over this infrared wavelength range from 1, this time all the way out to 15 microns. And the blue here is good. This is high transmission of light through the Earth's atmosphere. So there's our visible light spectrum, which we can see with our human eye. And this is all this wonderful infrared that we would like to study. These gaps here are literally places we can't look because of the opacity in the Earth's atmosphere absorbs all the light before it gets to us. And what is doing all of that absorbing? It's molecules in our Earth's atmosphere, which in part lead to our greenhouse effect, which we study. But also, we can't look at these transitions from the ground. We have to go to space and to study them. And many of them are exactly the kind of molecules you would like to study in planet atmospheres around other stars. So this is another reason the wavelength range we would like to study in space is a tremendous asset. There's also a technical reason why the fields of view we can access at this fine precision in space are better than we can do from the ground. It turns out that the precision that I demonstrated with this toaster and the small telescope here, we can do pretty well with an advanced technique called adaptive optics from the ground, but only on very tiny fields of view, one object at a time. Whereas in space, we get this full optimum fineness of detail over rather large fields of view. And for these three reasons, this facility is untouchable from the ground. It's really doing things in space we absolutely cannot do from the ground. So thus became the James Webb Space Telescope. And it's kind of an interesting philosophical discussion where you're designing a new facility, whether you go for that discovery space where you know there's stuff there because you've never been able to see it before, or you are refining a very specific experiment that you want to do. You have an hypothesis and you want to test it using the scientific method. These can be in tension with each other, because if you can design an experiment where you know exactly what the outcome might be, well, that is something that is known in a way. The discovery space argument is really exploration. I'm not necessarily forming hypotheses that I can test, but I know there's a lot out there to look. And both of these are used in designing a facility of the scope and majesty of something like the James Webb Space Telescope. It's a big, complicated, expensive proposition, and so it was decided immediately that international partners would be an important part of this. We're in this together. So NASA teamed up with the European Space Agency and the Canadian Space Agency to build the James Webb Space Telescope. Okay, so a little bit more about JWST. It has an interesting orbit, so it is being injected into an orbit, Lagrange point number 2 in our Sun-Earth system here. This is a semi-stable place where it's not perfectly stable, in that if you nudge it off where you want it to be, you need to bring it back. There are other Lagrange points, 4 and 5, where it's stable. If you nudge it a little bit, it pulls it back, but there's debris there. So those are not good places to put a telescope. There are lots of sun-observing satellites on this side of the Earth-Moon system, but L2 is where JWST, if you block out the light from the sun to help you see farther behind you, you also block out the Earth and the Moon, and so this is a very favorable place to put this kind of telescope. As I said before, it's primarily observing in the infrared region, so a little bit in the red visible, all the way into the near-infrared and mid-infrared, and it stops at about 25, 28 microns. This is the collecting area of the James Webb Space Telescope relative to the Hubble Space Telescope mirror, which is only 2.4 meters in diameter as opposed to 6.5 meters in diameter. And notice that it is segmented. There are many, many segments that form that giant aperture across here. And this is a novel thing for us to do in space with our kinds of telescopes that astronomers use. And there's an astronaut for scale. Okay. So now I would like to demonstrate, with the help of this infrared camera over here, partly why we're looking into the infrared, but also this idea that on one side of the telescope we have the sun, we're getting power from the sun, but we really need to block that sunlight from one side and that we can observe with our instruments from the other. So first of all, let me show you my hand through this bag. So this is a opaque trash bag that you can't see through with your eyes in visible wavelengths, but hopefully I can get enough contrast so that you can see my hand inside of this bag. Oh, maybe I'll do it from behind. It'll be better. Oh, I can't see so well. you can see through this bag. It's not an exact replica of why we look in the infrared in space, but it turns out that dust, the kinds of dust we need to fight with our astronomical observations in the space between the stars and in our galaxy, that dust is more transparent to infrared radiation. The scattering properties go down as you go to longer wavelengths, and so I can see deeper into clouds of gas and dust in space. So that's one reason why we go into the infrared. Here, as you can see in this diagram, we have what we call the cold side and the hot side of JWST. On the hot side, it gets pretty hot. 185 degrees Fahrenheit, and that's where the sun is. And there are solar panels to get energy that we store, but we also have to have this shield between the sun and our instruments and the stuff that we want to see, the telescope on the other side. So what you're seeing is kind of a sun here, our little cheap version of the sunshade right here, and this block of ice shown as very cold blue in this thermal infrared image. That's where the instruments are. That's where we're keeping our cold telescope and our cold cameras so that they operate with optimum efficiency. So this is a little camera that you can buy for about $10,000 that goes out to about 14 microns. And that is a heat-seeing camera. It kind of can see the heat that we are emitting and all around us, and people use it to look for places where the heat in their house is getting out or the cold from outside is getting in. These infrared wavelengths can trace temperatures, not unlike the temperature on our Earth at 300 degrees Kelvin. This camera is very sensitive to those wavelengths. That's why we use it. But there are a range of temperatures in the infrared that these kinds of heat-seeing cameras can trace. And this is what we are primarily studying with the James Webb Space Telescope, these infrared wavelengths. Okay. I'll say a little bit more about the sunshade in a minute because it is a technological marvel. The telescope is 6.5 meters in diameter, and in general, that is very large for the kinds of rocket shrouds that we can pack things into and send into space. So it was decided to fold up this mirror like an origami, pack it into the cone of that, and then we would have to deploy actively the edges of that telescope after launch. And this is a kind of a frightening proposition for an astronomer. Say, what? You're gonna break up my telescope into little pieces, fold it up into an origami and unfold it in space, by the way, where no astronauts can go out and help you if there's a problem. So this was very nerve-wracking, but so far everything has worked spectacularly. I can't show you pictures of JWST right now because it's gone. It's too far away. We can track it with telescopes as a point of light, but we can't take resolved images of the object itself. And this is one of the last images we have. This is taken from a camera on the upper stage rocket after separation, and the rocket's falling away, and there it goes. So this is sort of a beautiful postcard on Christmas Day of JWST going away from us, the last picture of it that we will see as a resolved object. Okay, so now I want to show this movie. Because I can't show you real pictures of the unfurling of the telescope, I have to rely on this film. So let me start the film. So there's our launch. We have vehicle separation, and there goes our space telescope out into space. Within the first 30 minutes, we needed to get that a solar array out there because we need power to do all the rest of the stuff that you're going to see. Fortunately, that worked well. That was the first milestone that we were worried about. And then subsequently, there's a tiny little rocket fire there to keep things on course. And slowly, over the next few days, there are many, many major deployments. The antenna, so that we can communicate with things in day 1 to day 2. Another tiny burn, mid-course correction. Now we're about as far away as Apollo 13 was, and we're going to go a whole lot farther away from the Earth right now. Now we need to unfold these pieces that are going to block the sun from our telescope. There are 2 pieces to the sunshade deployment on each side. So you'll see that. This is at about 3 days. And now we have to lift up the telescope. It can't sit on that platform. It's got to go up before we fold out the mirror side. So that had to happen properly, and it did. Each of these can be taking 1 to 2 days to complete. We take the cover off of the sunshade, And now the booms have to go out. So we're going to stretch out this sunshade, our umbrella against the sun. So we pull it out on each side and start to stretch out that thing. Then there are edges that need to come out as well. Now we have to tension this membrane because it needs to be taut and flat. And then we had to separate each layer. There are 5 layers that you see there. Each one is critical in removing half of the energy from one side of the sun to the other. So you get a factor of 2 to the 5 in the difference in the energy coming through. Now the secondary mirror boom has to be deployed. We're at day 11, if you can't see that. And the wings are coming out. So now my telescope, the sides of it are pulling out into place. Oh my goodness. Thank goodness that worked at day 14. And now there's another little burn, and we're getting close to where we're going to spend the rest of our days, we hope. And we're entering into this little orbit around the L2 point. Occasionally, there will need to be little rocket fires. This whole process, the fuel was conserved rather well. So we believe we have enough fuel for these little these course corrections in the L2 halo orbit for more than 10 years of operation easily. The requirement was 5, the goal was 10, but we should live well beyond that. So, some of you may remember the Perseverance Mars rover that had to go down through the atmosphere, an incredible landing on the surface of Mars. There was the so-called 7 minutes of terror as that little thing had to go down and go across the surface of Mars. This was literally 30 days of terror. There were so many things that could go wrong. You know, it's fun now to hype it and say, well, there were, 348 single-point failures. That's perhaps a bit of hyperbole, but there were a few dozen really important things that if they had gone wrong, this would have been really tough to recover from. Of course, one asks the chief engineers, what would you do if something bad happened? And they sort of hem and haw. You may have seen videos of them talking about this. They would shake it, basically, like you would do at home with your television or something. They basically would give it a good shake, and hopefully things would work again. Anyway, it's so far so good is all I can say. Part of the delays and the difficulties, it was incredible engineering. There were things that had to be figured out how to do, and that's expensive and it takes a long time. And of course, there was testing. As I said, astronauts could go out and save us from an error, so this had to work. And everything had to be tested, integrated, and then tested again with new components added. So this is the whole thing going into a thermal chamber and a vacuum chamber at Johnson Space Flight Center. Some of you may be old enough to remember that astronauts actually walked on the moon. And astronauts did walk in this vessel. They were fully suited and tested things out in here for Apollo. So this is still at Johnson, and we use the thing for JWST. An extension of the capabilities of this was to be able to go down to the operating temperature of JWST, which is about 30 degrees Kelvin. So way colder than it ever had to be before, minus 388 degrees Fahrenheit approximately. So this was an incredible effort by thousands and thousands of people all over the world to test and see that this thing would work properly. Okay. These are actual images from the James Webb Space Telescope, the Near-Infrared Camera that I was very fortunate to play a very small role in with a very large team. The Near-Infrared Camera, NearCam we call it, is responsible for helping the telescope figure out the figure and the quality of the mirror and to adjust all of the actuators to bring everything into sharp focus. So this is a bit confusing, but each one of these individual segments that you're seeing is seeing an image of the same star. And the plates of each piece of the mirror can be tilted in multiple orientations and out of focus, and the image is not even focusing where we want them to. And furthermore, all of the segments across the diameter of the aperture need to work in unison together. We're not there yet. But what has happened here is that we've been able to tip and tilt the individual images of each star onto the detector, which was a first huge success to get all the images. So each segment is making its own image of the star, 26 there you see, and now we're focusing up each individual image. So in this little animated GIF on the left, you see the unfocused images, and then zoom, everything comes into focus. Remember, this is all the same star. We're making individual images of each one. And then, just as we had done at a telescope in Arizona many years ago, we stack all the images. You make a movement of each of the mirrors so that all the images are overlapping on one, and that is the image that you're seeing on the right, the fully stacked images. But let me be clear, we're not done yet. There is very fine phase control and matching up that needs to happen on these mirror segments, which has not been done yet. It will take a couple more months. We're simply stacking the images sort of roughly. When the telescope was deployed, the mirror segments had uncertainties in their position of order a millimeter. So a tiny, a fraction of an inch. And to get the fine images, the ultimate quality images that we anticipate, we need to go down to 50 nanometers. So that's about 10 to 20 hydrogen atoms stacked up again and again on each other, just for comparison. So a few dozen hydrogen atoms stacked together would be about that size. So we have the stacking, and we're getting good images as we go, but we've still got a long way to go for the fine phasing. There's a very clever way using a pupil imaging mode with prisms where we can adjust in very sensitive detail the phases across each surface, and that will take a couple more months to do. Okay, so back to the astronomy a little bit and what we're hoping to get from this telescope. As I said, we are focused on the infrared part of the spectrum, and there's a Y there, which I sort of mentioned already. One reason is that there are many cool objects in the universe, pun intended. Planets emit at these wavelengths with temperatures that JWST is exquisitely sensitive at seeing. So we can look at cool objects, temperatures below 3,000 degrees Kelvin, at the faintest edge of stars, all the way down to planets and asteroids. Intrinsically cold objects, JWST is terrific at looking at them. There are also objects embedded in dust in space, and as I tried to demonstrate with the trash bag before, the infrared wavelengths can penetrate more easily through the dust, allowing us to see stars and planets in formation. This is an image of a disk around a young star. The hole in the middle, the star has been masked out for your viewing pleasure, and this is scattered light from dusty particles in the disk. This is a planet forming within that disk, which is glowing from its own infrared radiation. So we are just having the ability for the first time to study planets while they are actually forming in gas and dust-rich disks around stars like the sun. And as I mentioned before, due to the expansion of the universe, looking back in time requires us to look at infrared wavelengths. And as I said, Hubble kind of hit a wall of what it can see at about 1 billion years since the Big Bang. We should be able to go significantly farther than that with the James Webb Space Telescope. And when I started thinking about this project, my expertise are down here. Everyone was only focused on this, and the main goal was to look for first light. Could we see the very first stars and galaxies with active galactic nuclei or black holes forming with them? Could we see those first objects forming and emitting light in the early universe? And that is one of the main goals of JWST, but we've extended the mission to look at these other classes of objects as well. So this is kind of a visual demonstration of why infrared. This is an image of a region where young stars are forming. The darker regions are where dust is blocking out the light from behind it, and the blue and green glow is a hot gas where different elements are emitting their characteristic transitions of their structure, and that light is coming through and being blocked by these pillars of gas and dust with the infrared passing through a little bit easier. So this is the same region now seen in infrared light, and you see it's full of stars, as the quote goes, toggling back and forth between the visual image and the infrared. It is just a very different picture of the universe that you get. This is the Eagle Nebula. These are the so-called pillars of creation, and we're able to see young stars forming in the infrared in that region. Okay, so here are the wavelengths shown against the 4 science instruments on the telescope itself that are taking data or will take data. The Canadian Space Agency funded and led the NEARIS instrument and the Fine Guidance Sensor, and my group was involved very lightly in that. The European Space Agency was primarily responsible for the near-infrared multi-object spectrograph, where you can take spectra of hundreds of objects at one time with their cameras. NearCam is the one that was led at the University of Arizona when I was on the faculty there. And the principal investigator, the woman who conceived the whole thing, was born and raised in Midland, just for local interest. So Marcia Ricci, a tremendous leader in our field in infrared astronomy, she's a Michigander, so that's a local connection as well. And then MIRI is a mid-infrared camera. It's a collaboration between NASA and the European Space Agency. I had the good fortune to be able to write up the science requirements early on for what that instrument should look like. And that was a real privilege to be involved in that. Okay, so these are the instruments kind of packed up into the business end of the observatory behind the telescope, which you're sort of seeing here in what we call the ISIM, the Integrated Science Instrument Module. And they all have slightly different positions. They share the focal plane of the telescope. And different ones of them, these icons are meant to represent whether they have an imaging capability. This prism is meant to indicate that we can break out the light into its constituent wavelengths and take spectra. So you're breaking up the light and looking at the different wavelengths and hopefully seeing signatures of atoms and molecules that you can identify through spectroscopy. And then this funny star with a hole in it, those are coronagraphs. They are special technical optical elements to block out the light from the central star so that we can see faint things very close to bright things. And each of the instruments has different combinations of cameras and spectrographs. All right, moving on to the science. Not conceived of when the James Webb Space Telescope was designed was the explosion in understanding planets around normal stars other than the sun. The first one was discovered in 1995, and so that started a revolution in the field, which is still ongoing. But James Webb will be an excellent tool to study the atmospheres of these planets. As a planet passes in front of a star, you don't see the picture of this, but you see the light dimming. And planets of different size relative to the size of the star have different amounts of dipping. So an Earth-sized planet makes a smaller dip. Oops, sorry. An Earth-sized planet makes a small dip, and a Jupiter-sized planet makes a subsequently bigger dip because the radius of Jupiter is larger than that of Earth. We can go one step further, and Kepler and many other telescopes have found thousands, that we have now over 4,000. We're closing in on 5,000 planets around other stars right now. And a tremendous diversity. I can't tell you how many surprises there have been. The first one was a Jupiter planet in a 4-day orbit, well inside the orbit of Mercury. Compared to our own solar system. So wild, crazy, unexpected architectures of these planetary systems. This is an example of planets around a star on the edge of being a star. It's a so-called failed star, a brown dwarf, where it will never reach the temperature high enough in its core to fuse hydrogen into helium. It's right on the boundary between being a star and not a star. Turns out there's 7 planets in that system, and a few of them could exist in its liquid water zone, where water would be in liquid form on the surface of a solid body at its distance from its star. With these transiting planets, you can break up those shadows or transits into the different wavelengths of light, and it turns out whether the molecules or atoms are absorbing or not, the artificial radius you would derive gets bigger or smaller due to the opacity of different elements in the atmosphere. So by taking transit measurements at different wavelengths, you can reconstruct a transmission spectrum of the object. And we can look for these different molecules in the atmospheres of these planets. And because some of these planets might be in the liquid water zone, one is tempted to, number one, look and confirm the water, but number two, to look for other organic molecules of interest in the spectrum of these objects. I have to stress, this is a very, very difficult measurement. It really is pushing the detectors to the stability, the edge of their stability. They weren't necessarily required to perform at that level, so we'll see how well we do. But this is an incredibly exciting way to get a first glimpse at the compositions of Earth-like worlds which might be in the liquid water zones of their stars. But we will maybe make one observation like this. It'll be that tough to do for an Earth-sized planet around a very, very small star. My colleague Emily Rauscher in the astronomy department is an expert at studying the atmospheres of Jupiter planets, their temperatures, their heat redistributions, and really their wind speeds and climates. So she has 3-dimensional climate models of these other worlds, and she's heavily involved with some of these programs. We have many researchers in our department who study the formation of planets around young stars. As I mentioned before, this is a forming planet in this circumstellar disk of gas and dust around a star with the unimaginative name of PDS 70, but there will be many observations of objects like this. We are able to see brown dwarfs, these so-called failed stars, with Hubble and with other ground-based telescopes, but with JWST, we will be able to go down to planets. In special cases, we'll be able to see planets as low in mass as Uranus and Neptune. And this is a real revolution in our ability to take pictures of planets in the wide orbits around their nearby stars. We'll be having many studies of stars and brown dwarfs with the James Webb Space Telescope, and many of us here at Michigan are involved in those. We'll be studying how the winds and supernovae of stars, massive stars, sculpt the energy in the interstellar medium, rearrange stuff in the galaxy, and trigger the formation of the next generation of stars, and how the energetics of the interstellar medium are mediated by the atoms and molecules and structures of dust in their vicinity. And we'll also be able to understand the end states of stars, to look at objects like black holes, and in particular black holes that are co-evolving in other galaxies, the so-called supermassive black holes, like we have one in the center of our galaxy. It seems that there's an intimate dance that black holes and their host galaxies do in their evolutions over billions of years, so we'll make major progress, and that's a focus of our research department here at Michigan as well. As I said before, the real goal is to try to look back at first light in cosmic time. Can you see the first stars and black holes forming in the first galaxies? We are at this edge of redshift 6 or 7, which has a look-back time of about when the universe was, say, 800 million years old. We ought to be able to go back to several hundreds of thousands of years, millions of years, tens of millions of years, hundreds of millions of years. There's a whole range of time. We won't get all the way back to the cosmic microwave background radiation at 380,000 years, but there's a big space between 380,000 and 1 billion. And so we will be able to chart how these early galaxies formed and evolved by looking at very, very distant objects, which again is looking back in time. And there's a special trick we can use, and my colleague Karen Chiron uses this trick called gravitational lensing, where you see this amazing picture. These arclets that you see, this light being stretched out into a circle, is a consequence of Einstein's general relativity, where a huge amount of mass, which is telling the space near it how to move, is actually bending the light that would have missed the Earth back towards us. And by studying objects using gravitational lensing, we can actually look back much farther than we could have, and at finer spatial resolution than we would be able to without these gravitational lenses, or giant nature telescopes, if you will. So Karen and her colleagues are able to study star formation in the very, very earliest phases of the universe evolution using gravitational lensing. And JWST, like HST, will be exquisite for this kind of work. So it's a very exciting new step forward in the capabilities of Karen and her colleagues. So the James Webb Space Telescope, it's not just me, it's not just Emily, it's not just Karen who are involved. This is a list of all the people I could think of in our department who are involved in the James Webb Space Telescope in one way, shape, or form. It's over half of the research groups in our Department of Astronomy, and we've tried to list some of the postdocs and graduate students that are involved. And I highlight Larissa Marquardt here in bold because she is one of the very few people as a graduate student who was able to get time on the James Webb Space Telescope through the International Cycle 1 competition. The oversubscription rate was a factor of 4 or 5, so fewer than 20% of the proposals got time. And Larissa, she's not done with her PhD yet, but she's one of the lucky few who got time. So we're very proud of her and her team that got that program forward. But we're part of dozens of these and leading several here at Michigan, which is an exciting opportunity for us to lead in taking this next step forward. Well, JWST is not the end. It's just the beginning in some ways, but it's a major milestone in the kind of space astronomy and infrared space astronomy that people like me want to do. We've just gone through a several years exercise of planning and prioritizing the next decade of astronomy in the United States. This is a process we do every 10 years, and if I'm not mistaken, we started it back in the early 70s to do the first National Academy-sponsored decadal survey of our field. And the idea was that You know, we are very grateful for taxpayers' funds to allow us to do the research that we're doing, and we feel that we should prioritize the things that are more important rather than less. We can't do everything, although we'd love to, but it would be nice if our policymakers had a guide or a booklet that they could look to and see what our priorities ought to be when the funding decisions get made. So this report came out in November of last year, and there are lots of exciting ideas going forward. One of them that's already in progress that you'll hear more about in coming years is the Nancy Grace Roman Space Telescope. This will be launched in 2025, and it has a special mission to map the whole universe instead of just looking at special points, but to do an amazing job of trying to map large sections of the sky to study cosmology and the equation of state of dark energy going forward. There are other special opportunities for other astronomers as well, but we're very excited about the Roman telescope going forward. Named after a space scientist who led the development of Hubble in the early days in the 1960s, Nancy Grace Roman. One of the flagships that's been considered for the next decade and beyond is some 6-meter replacement for the Hubble Space Telescope. We call it HabX or LUVOIR or some combination of those acronyms because it is meant to try to take pictures in reflected light of an Earth-like planet around the very nearest stars to the sun. This is something that we imagine will go out several decades. It's not going to launch 10 years from now, but it's probably something that would launch in the late 2030s or 2040s. And James Webb is a step on the road to that. And if these things all happen on schedule, the next mission that I'm at least advising in this early stage is something called LIFE. This would be a mid-infrared telescope like JWST, but it would be free-flying elements of an interferometer. They would have to get several hundred meters up to a kilometer across, and in the mid-infrared at 10 microns, they'd be able to take pictures of the thermal emission of a planet like Earth around a nearby star. And if you're able to get the reflected light of an Earth-like planet, as well as the mid-infrared thermal emission, you can do something that we call resolving the radius albedo ambiguity, where we can understand how reflective something is versus how much energy it absorbs versus how much energy is being re-emitted. And these are the elements you need in order to know whether a planet has an active greenhouse. We may or may not see biosignatures and signs of life, but we can definitely characterize the diversity of atmospheres around these other Earth-like worlds in the near environment of the sun. So that is a quick tour of what we are hoping to get from the James Webb Space Telescope. It has been a remarkable ride. There have been moments of uncertainty, but there is an unbelievably dedicated team of thousands of people who have made this work and who are right now, staying up in 36-hour shifts to make sure that nothing goes wrong in the final phases of commissioning. And hopefully you will see some first real science images in late May or early June. Thank you very much.
Well, thank you very much, Michael, for that really wonderful presentation and explanation of many things. We have some questions to start, and maybe more will come in as we go here. So in the beginning, you talked about designing for discovery versus designing to test a hypothesis testing. Can you give an example of hypothesis testing that's in the design?
Well, something we argued a lot about was exactly how many objects per square arc minute or per degree on the sky there would be at redshift of 12 to 17. And so if you look for them and you don't see them, then you would rule out elements of that cosmological theory that would form objects with a certain frequency at those stages. And that was a place where we got into real trouble because the density of those objects on the sky was very difficult to predict, and then the instruments that we would design had to match the density of those objects, and in particular, the multi-object spectrograph. NearSpec is capable of taking several hundred spectra within a, say, 2 by 4 arc-minute field, and if those objects aren't there, maybe there's only one, you should have designed a slit spectrograph that would maybe be more efficient or better. So this was a place where the engineering design of what we could do was being influenced by an astrophysical theory but it was uncertain enough that you were kind of, you couldn't say, like you might with the microwave anisotropy probe in space, that you have a very specific prediction of what the power spectrum of the microwave background looks like, and if you see this, that, or the other thing, you will make serious progress. This was a very much an iterative process where we saw what the instruments could do, asked what kinds of measurements they could make, and tried to collide those predictions with capabilities. In the end, you end up trying to be flexible against a range of possibilities that you think are plausible, and then try to go in deep in this discovery space as you could.
Okay, great. So here's a question. I guess maybe it's the sociology of science. I'm not sure, but are the data that are coming from this telescope, are they open data? Or do people, well, how does it work? Do people actually have to apply for observation time, write proposals, et cetera?
That's a great question. So those of us who were involved in one way or another in the mission early on, for example, Marcia Ricci and her camera team, we were awarded 900 hours of guaranteed observing time as a reward for 25 years of science and engineering to build the camera. And that's great, and it was a great motivator for us to write that original proposal in 2001 to 2003. So those are our data, and we get them for a proprietary period of 1 year after they're taken so that we can try to do some early science with the instrument that we were involved with building. The cycle one, every year there's hopefully, or every other year, there will be a call for proposals, and anyone can apply to use the telescope. The oversubscription rate right now, because I think people were nervous and they felt it was a brand new thing and they didn't exactly know maybe how to use it, the oversubscription rate was only 4 or 5 to 1. We expect the oversubscription rate will skyrocket in the coming cycles, so maybe 10 to 1. Like Hubble is, would be a very typical oversubscription rate. So only a few people will get their programs. They will get to decide what the telescope looks at. There will be a small proprietary period for those data, but then everything becomes public. And anyone can go into the archive and download these data. And that's true for all of NASA missions. There's a pressure to get the data out into the general public's hands as soon as possible. And that is an evolving policy at NASA right now. But right now, we get a 1-year proprietary period.
I'm just wondering if anyone in the world could go into that archive. You don't actually have to have an email address or something like that. There's certain countries that are the stakeholders.
No, anyone can go into it. And of course, there are some logistical issues. I think they will ask you to register and form an account, just like you might have to accept cookies with whatever other applications you're using. But in principle, anyone in the world can get those data. And that's true for all of the NASA archives.
So awesome to keep science international. So this is just related, but to the last two questions, really. How is time prioritized for pure exploration versus scientific method experiments, hypothesis testing? Or maybe a better question is, who reviews the requests?
Well, it is an interesting question, because as things get more competitive, then one tends to fall back more, properly so in my opinion, on the proper scientific method and distinguishing the hypotheses that one could test. And so as the proposal pressure gets to be 10 to 1, I think you will find people being more conservative in what they will propose. And so they will be looking for the highest impact experiments, quotes unquote, that can be done, but that are still very feasible and not high risk. I think when a precious resource like this becomes available, you don't want to take too many risks, even though you know the very best discovery you might make would be in the space where you're taking huge risks, but it's expensive. So that's a big tension. On the GTO teams, because we get 900 hours up front and no one really gets to tell us what to do, we see it as our job to take a little bit more risk. So we should try to design experiments to push the cameras to the limit of what they could do, and then provide kind of a pathway for future community members to propose things that we've already demonstrated are feasible.
Okay. There are a lot of technical questions in this fascinating instrument that's been developed. But maybe I'll start here. What are the dangers that are in space now that it's there and for the next 5 and 10 years, such as cosmic rays or debris, et cetera?
I myself don't know the details of the debris environment. I mean, I don't expect that they are very high, but of course there can always be a micrometeoroid that can fly by. Certainly cosmic rays are an issue, and that is definitely taken into account in the exposure times that we are allowed to take. So a typical exposure would be limited at about 1,000 seconds because of the cosmic ray hit rate and how many times a cosmic ray would impact one of our camera fields of view. So that is known and taken into account. The detectors that we have are relatively robust against cosmic rays. You can zap one of the pixels, and it may take some time to recover, but it is very unlikely for anything electrical to come because we sort of keep the voltages of the pixels at very high, and as they accumulate charge, they drain down to zero. So in these kinds of infrared detectors, they don't have particularly dangerous electrical problems. I think it's more we would be concerned, the biggest worries that I have are simply mechanical. If something were to fail on the observatory, it could be game over for one of the instruments. There's a contamination control cover on the mid-infrared camera that when it's changing temperature, you are worried about things condensing on the lens, and so you close it and then you open it up again. That's a single point failure you'd be quite worried about. A filter wheel could stop moving, and then you're stuck in that one filter for the next 5 years. That's devastating to people who design the camera. So I'm personally more concerned about moving parts on the observatory itself.
Lots of moving parts. About the image adjustment, so going from 1 millimeter to 50 microns, that's done mechanically with these individual pieces, or is that sort of a software thing?
No, there are a large number of actuators that are all over each of the segments, and they are moved just so to try to get to 50 nanometers. I mean, it's almost unbelievable that you would try to do that, but that is exactly what we are hoping to do. We're not there yet, but we'll see what the final image quality is. We will still use software and information theory modeling to try to improve the quality of the images to the ultimate limit. But the better the phase control on the mirror is when you start, the better the software techniques will work downstream.
I guess this is, maybe you just answered this, but in terms of image adjustment, is this something that's done in real time? Are there like control systems that do this?
There are multiple.
Or are there engineers?
There are multiple layers. Once a month, you might really shut down the telescope from observing and take some time to really go through all of the adjustments you might make. We generally would do a phasing calibration every 2 days to try to retain the figure of the mirror. Things will drift thermally over time. There are certain orientations where the thing will heat up a few more degrees than in other orientations, and all of this is taken into account in a thermal model. But you would tune up the major figure of the mirror every 2 days and then hope for the best in between time. We actually have a calibration program where we would take data before a tune-up and after a tune-up, and then before and after the next tune-up to try to see what the drifts might be in between so we could build a predictive model that would sort of knit together calibrations on either side as priors into a model that you might make to improve the outcomes in your post-processing.
So are you looking at a star or something like that and just trying to make it perfect?
Fields of stars. So we generally have calibration fields with as many stars as we could fit all across the field of view from one corner to the other, and we would use that to try as a calibration. We go back to the same region over and over again. It's not only one region, because there's also issues of slewing and time to slew around the sky, and at different times of the year, because we're in L2, we'll be pointing around at different parts of the sky. So we have to pick calibration fields all over the place, but we still try to go back to the same ones as often as we can.
I want to remind the audience here that if you have questions, you can put them on a card, and Professor Roy Clark, will collect them. So let us know. Let's see. So, back to technical questions. Is there an electric power source other than solar on this satellite telescope?
There was a battery that started the thing, and that could go, I think it's an hour or two, but it really wasn't many times longer than that first solar array deployment was. I am not an expert, so I don't know, but I suspect there are a couple of backup batteries that if the solar array power supply was failing for some reason, there would be a period where we could continue to operate and then try some, shake it again, try some things to get the solar array working. But I don't know the details.
But there is another question about the solar panels, which may also be expert, which is what is the nature of the solar panels? In particular, are they like the ones on our house? Are they made of silicon? Are there special materials?
I suspect they are made of special materials, but I am not an expert on the solar arrays. I don't actually know what they're for. Someone in the audience there's been a huge amount of progress in this field, I think, in the last 20 years, and so I think there are much more efficient materials nowadays. My guess is that space-qualified solar arrays are previous generations by a few, because they had to be space-qualified, and so I'm sure it's not the latest, most efficient material, but again, I don't know the details.
So one of the questions was about the test in that chamber of the unfolding the mirror. And so the vacuum and temperature are apparently quite important. But what about microgravity versus here on Earth?
That was the thing we couldn't test. We just simply couldn't do it, right? I mean, we were here on Earth, and all of this phasing of the mirrors that you're talking about, that had to be done under Earth's gravity. And there's a beautiful 1/6 scale model of the whole thing with the subapertures and exactly the same alignment procedure that will be used with the grisms and the pupil plane phasing. Everything was done in micro scale, but it was done in Earth's gravity. And so this is the thing they're testing right now that could not be tested in advance.
Would you anticipate big differences?
I mean, every device, of course, will have different forces on it, right, in space. So, and of course, there are many decades of moving mechanisms in space, and people who are smarter than me know how to handle that, I'm sure. But I don't know that I would expect particular differences. But they did their best to try to take everything into account.
So the data that come, how are they transmitted? Obviously by some kind of radio transmission, but it's some special digital.
So it's a standard space digital communication. There's a deep space network. And it turns out there was some interesting issues with the bandwidth that you can get. So when we are typing in our programs into these preparatory algorithms that create templates to issue commands to the telescope, you often get this yellow and then red, data volume exceeded, because I really wanted to take a certain number of exposures, extra calibration, this or that, but you get, your hand slapped with a ruler that you need to cut this down a little bit and make it a little bit easier for the telescope to get the data. I think it's 223 gigabytes per day is the data rate that they expect. There's continuous coverage of the deep space network. One nice thing is it's always, apart from the sun, and so there's continuous coverage around the globe. But there are some times when they just need to send commands. They can do that at low baud rate, but when they need to really download a lot of data, they have to use I think it's called the Ka band of the deep space network for high bandwidth transmission, and there's a limit to that.
I see. So turning them into images, that's done on the Earth?
There's a solid state recorder that collects the data in principle. Not every raw image is saved and sent down. So there's a very tiny amount of co-adding and post-processing that's done to get. And this is kind of the issue. When I'm taking data, I want every single image of everything. I want every electron, because something can go wrong, and I want to have the ability to post-process it, but we can't do that. So these particular detectors, you are collecting a signal as you go, and you can actually sample the signal at multiple times before you destructively read out the device. And what we're really calculating is the slope over time of the signal growth. So what do you take? Do you take each sample? Do you only take the slope and an uncertainty? Big debates about how you package that data, fighting between wanting everything and preserving the bandwidth. And different readout modes collect different amounts of data.
Sounds like fun. Okay, so I think that's the technical questions. Let me just check here.
We're going to move into philosophy after.
Well, we're going to move into politics.
Oh my gosh! Okay, religion, politics. What else do we have here?
Well, we're back to science. All right. So the question is: was it hard to keep this going through many administrations and Congresses and changes of parties, et cetera?
Well, yes, some of you must know the backstories here. There was a real near-death experience in 2011. There was a strong move to cancel the thing, and there were people in Congress who decided that was a bad idea. Of course, if things are going off the rails and at some point you feel like you're throwing good money after bad, you have to seriously consider whether you would cancel a project that is facing challenges. But if you can convince people that you know that there were issues in the past and you've got a good path forward, we've spent this money already, we believe we can produce this incredible facility, you try to soldier on. And that needs defenders, and there was one, Senator Barbara Mikulski, who is a very prominent defender of the space program in Congress, or was, and so she was very helpful and strategic in helping to keep the James Webb Space Telescope program alive at a very difficult time more than 10 years ago.
Well, thanks. I guess the final question goes to your last slide that showed ideas for future missions. The question is, what is the time scale? When would the next one of those space telescopes or following missions be launched?
Well, as I mentioned, the Nancy Grace Roman telescope is already, past its critical design review. It's in phase DE. They're cutting metal and building it right now, and it's going well. That should be launched in 2025. I'm not going to say it won't slip to 2026. I mean, this game, you have to be patient. These next generation of facilities are going to take a while. They're very expensive. They're very, very complicated. The plan now is to enter into something called the Great Observatories Technology Maturation Program, to ask the question, if we spent $100 million now in this, and this, how many billions could we save down the road? What risk can we buy down? What science would make the experiments that we want to do more tractable? And so are there cheaper and easier ways to move the ball down the field before you really commit to a $20 billion observatory? So that's part of the process we're starting right now. The other thing I would say is it does depend on the state of the budget. We have had a period where there have been investments made in infrastructure, which in Michigan, I think we all know we need good roads and other safe bridges and things. But if there's a part of investing in our future that includes space exploration and NASA, relatively modest increases in a NASA budget would bring the time horizon from 2040 down to 2030 very easily. And so if people were interested in having a great observatories program, as we did in the 1980s and 90s, which gave us the Hubble Space Telescope, the Chandra X-ray Observatory, the Compton Gamma Ray Telescope, and the Spitzer Infrared Space Telescope, we have missions ready to think about now that we could move forward on and recreate that flotilla of science exploration in all the wave bands of interest now, that we could do that in the next 20 years if people were willing to tolerate a raise in the NASA space science budget that wouldn't even come close to being compared to the manned program, of course, not to mention our defense budget and other elements of the federal budget that are large.
Interesting relativism that maybe isn't that easy to do. Do you have one or more examples of spin-offs from the technology that's been developed over, I guess, a couple of decades now? Infrared cameras, maybe, et cetera.
Yeah, I mean, one kind of obvious one that I know from the infrared detector development. To be clear, a lot of the big, heavy money development in infrared detectors comes from people interested in looking at their enemies and things like that. So the military obviously spends a huge amount in developing infrared detectors. But one of the main companies that we worked with in Arizona, Infrared Labs, was led by an infrared astronomer who had a spin-off that was able to use very high speed, very high quality imagery of solid state wafer production, and was able to detect hairline fractures in a very major production line that was very important for some segments of the solid state chip community. So that's one that I just know of personally. Frank Lowe, who passed away a number of years ago, was a visionary and a pioneer in infrared astronomy. There are a huge number of materials that are suited for space, which we use for other uses here on the ground. And where's my phone? I think all of you do know that the Apollo astronauts used a computer technology that was inferior to your smartphones by a lot right now. So a lot of what NASA was doing in the 60s was also in 70s, very important for the development of our modern computer age, not to mention the internet and other forms of communication. But I'm not an expert on some of those technology transfers. But it's very important to consider that. I totally agree.
Okay, great. Well, I don't have any more questions, so I would like everybody to thank Professor Michael Meyer one more time for a great lecture and discussion.